behind you actually. Literally, you came into our class.
Hi, everyone. So welcome to Physics Club. So we're quite happy to have Kyle Leach here. He's going to be telling us about hunting for ghosts using rare isotope dope superconducting and optomechanical sensors. So Kyle did his PhD at the University of Guelph in 2013, then moved to Triumph, which is the kind of premier accelerator laboratory in Canada for a postdoc, and became a faculty member at Colorado School of Mines in 2015. As you're here, he's using these kinds of very fancy isotopes, and in fact, also has an appointment at the facility for Rare Isotope Beams, FRIB, at MSU, which is this brand new facility to explore the nuclear chart in a way we've never before. So to make all these exciting isotopes we haven't been able to get our hands on. And Kyle's really been a leader in taking those kinds of isotopes, pairing them with the precision tools we're making in AMO physics and with superconducting sensors to do very precise measurements of these. So he'll tell us a little more about that. Also mentioned he's got lots of awards, so I'll highlight a couple, including the DOE Early Career Award in 2020. And then he has one of these very fancy Experimental Physics Investigator Awards from the Gordon and Betty Moore Foundation, which are a nice kind of way to get money in your mid-career to do all kinds of exciting things that maybe are otherwise hard to get funded. So
I mean, crazy things.
Yeah, crazy things, exactly. So we'll be hearing about those exciting and crazy things here. Thanks, Kyle.
Perfect. Thanks a lot. So it's a great pleasure to be here. So like Dave said, basically the crux of the talk is going to focus on our ability to use these so-called rare isotopes, and I'll define what rare isotopes are, using modern sort of AMO-style high-sensitive quantum sensing and superconducting sensing techniques. So the first thing I'm going to do is kind of paint a little bit of an overview of the broad scope of what it is that we try to do and where we try to intersect with a number of other fields. So this is quite a nice picture, I think, that the NSF generated years ago, where try to get rid of that thing on the top, where basically it kind of gives an idea of a picture of what the cosmic history of our universe looks like. So there's something that we think looks like the Big Bang. We don't really know what that is in detail. There's something here that we call the cosmic microwave background, which is our plane of last scattering, where basically the universe had cooled sufficiently that light is able to free stream following this. We then end up at a period where we have a hot, dense universe that's kind of filled with gas. And over a period of many millions of years, we start getting something that starts to condense into galaxies, and then we have an evolution of our universe. We think we understand this within some kind of a standard cosmological model. But one of the ways that we do this is we start using our astrophysical probes, and we start looking further and further back towards the Big Bang. So you can think of things that look like ground-based observatories. Eventually you get to Hubble, and now we have the Webb telescope that basically starts to look closer and closer back towards the Big Bang. So just as one kind of little tidbit here, this here is actually the highest redshift galaxy that's been observed. And so this is more or less a couple 100 million years after the Big Bang. This is something recent that the Webb telescope has found. But at some point, you can't look any further back to the early universe using photons. So this is a picture of the cosmic microwave background. This is our plane of last scattering, like I said, where the universe had cooled sufficiently that light is able to escape. This is about 380,000 years after the Big Bang. But using photons, we can't look any further back than this, simply because this is the limit to where that information exists. Now, one of the other things that you can think about is you can start thinking about going... I think we've lost our connection here. Is that a Zoom thing?
This computer might be frozen.
Is that the computer that controls the screen?
Appears to be. So we probably need Jen's help for this. No, Jen, you're online. Could you come help? The computer's frozen.
Try.
Try that. May not be hearing it, she's on Zoom.
If I could.
into the laptop. Oh, the whole thing is frozen.
Oh, yeah, apologies, everyone. I think the room system is frozen, so we'll need the experts.
All right, I'm gonna grab some more coffee then. Okay. I'm happy to answer questions if people have other questions. I could move to the blackboard. Unfortunately, I have all these fancy images that ChatGPT made for me that I can't, it'll take me. describe the fundamental nature of our universe. So one of the things we can do is we can use things like gravitationally lensed images. So this is one that the Hubble has taken fairly recently. And we can start setting things like limits on the existence of new physics and new physics that can connect itself to our standard model of particle physics as well. So this is one of them that basically looks at the lensing profile and shows that there is some astrophysical preference for sort of light wave-like dark matter over dark matter that's more particle-like. And we can also look with the Webb telescope very far back to the early parts of our universe, sort of towards this plane of last scattering. And what is starting to be seen is that there's large-scale galaxy formation much earlier than things like standard cosmology would allow. So these basically paint a picture that there are things happening, and we're starting to build a picture observationally of the large-scale parts of our universe that we don't really fully understand because our measurement tools have gotten so good. Now, this also means that it provides us with an excellent connection back to the laboratory experiments that we do here on Earth. So ultimately, what we want to do is we want to take all of this information that we have about the large-scale structures of our universe, we want to feed them through this standard cosmological model into things that we can try to probe on Earth in a more controlled manner, and we can then use our standard model of particle physics to try to create a complete picture, ultimately, of a description of our universe that we think matches what we see. So this brings us to the standard model of particle physics. So here's a picture of the standard model particles. I won't go into them in any great detail except for the ones that I plan on discussing. But there are force carriers. So these are the bosons in the model. There are things that make up atoms. So these are our up quarks, down quarks, and electrons. I'll talk a little bit more about that tomorrow in the Right Lab seminar. We have neutrinos, which I'll talk extensively about today. These are the second most abundant form of matter in our universe next to photons. These are neutral left-handed fermions. I'll talk a little bit more about what that means in a minute. And the rest of the things are exotic and short-lived. They're integral to the creation of the standard model. But from a laboratory perspective where we try to probe and test things, because these are so short-lived and difficult to make, oftentimes for some of the precision measurements that we're talking about, we typically don't use these types of particles in our standard model. So I'm going to focus primarily on these neutrinos. So these are sort of the ghost in the ghost particles, simply because they're extremely weakly interacting. And they're one of the best windows into the fabric of our universe and a real connection between cosmology and laboratory measurements that we can do. Now, when I say they're ghost particles, what do I mean by that? And the fact that they're the second most abundant form of matter in our universe. So these neutrinos that were created at the Big Bang, these are extremely abundant in our universe. In fact, the number density of them here at any point in the universe is extremely high. However, the interaction cross sections for these are extremely small. This is in millibarns, and this number here says 10 to the minus 31. So the cross section for observation of these is extremely small. So they pass through us, and we are unable to detect them. However, one of the questions you can ask is, how are these particles that are so abundant in nature, carry so much information about the cosmological history of our universe, but are so weakly interacting? It points to the fact that we don't fundamentally understand much about the neutrinos at all, simply because they're very hard to detect. And so we need a much better understanding of these fundamental particles that can potentially connect us to cosmology through laboratory-based measurements, as hard as they may be. Now, neutrinos may, in fact, be connected to some of these big open questions. What is dark matter? Why does our universe contain an abundance of matter over antimatter? What happened very close to the Big Bang? And why does time seem to have some direction? So these main questions can be addressed in principle based on some of the understandings that we have about the neutrinos within and outside of our standard model. But in the end, we need to be strategic in the way that we search for new physics. So we need to find targeted areas that we can exploit in the laboratory that draw a definite connection back to cosmology and provide us with, as much as we can, model-independent results that basically can eliminate these kind of anomalies that we see in our current description. This is actually a slide I stole from Dave. One of the things that we've historically done in our searches for beyond standard model of particle physics, is we search for new particles at the energy frontier. We try to create them in the laboratory at the highest energies. However, there's another domain, which is the one I'm going to talk about today, that is exploited quite well here at Yale as well, which is the precision frontier. Basically, where you go to such precise measurements in the laboratory that new physics elucidates itself as a tiny little difference from the prediction that you would expect from the standard model, rather than trying to create the particles directly. And so people do this in a number of different ways. You can go to very, very high precision measurements of frequencies. So if you can convert something to a frequency, you can make a high precision measurement. You can also start playing uniquely quantum mechanical tricks in the so-called quantum sensing regime as well. So the way that we do this is we take unstable nuclei, I'll call these rare isotopes, which I'll mention on the next slide, and we use superconducting sensing technology, and as I may or may not have time to talk about at the very end, these optomechanical quantum systems that are being developed here at Yale. So what do I mean when I say rare isotope? So here's a periodic table. The elements on the periodic table are determined by the number of protons in the nucleus. So if I look at beryllium, for example, beryllium will be an important one because I'm going to talk about beryllium a lot today. Beryllium-9 has 4 protons and 5 neutrons. It is stable. Typically, that's what we think about as beryllium on our periodic table. However, you can continually take away or add neutrons to beryllium-9, and you can get a number of different isotopes, all of which are still beryllium, but they are rare in the sense that you cannot find these other isotopes naturally on Earth. Typically, we're in the process of trying to define what rare isotope actually means. I think we've more or less settled on the fact that we're thinking about something that has a relative natural abundance of less than a part per billion. And so in these cases, these are radioactive. So you must create them and then they decay. So there's a 0% chance effectively of finding them on Earth. So these are not naturally found on Earth. We call them rare isotopes. They are typically unstable, means they undergo radioactive decay, and that means we have to produce them in the lab. Now, why would I care about doing things that undergo radioactive decay? It's hard to produce. They're not found very naturally, and there's obviously health risks and things like that associated with doing experiments related to them. So I claim that nuclear beta decay and electron capture decay are among the most sensitive beyond standard model physics probes. To start with, they have pure energy to matter conversion, and they couple to all 4 of the fundamental forces. So let's take here the decay of the free neutron. So the neutron will decay to the proton. There is some mass difference between the neutron and proton, which allows this process to occur. But you can see that it couples, basically you flip a down quark to an up quark, but it couples to a number of the fundamental forces. And if you can make that measurement precise enough, you have access to all new physics that couples to those fundamental forces within that energy range between the mass differences, in this case, of the proton and neutron. Many of these systems are complex, but they're well understood. A lot of them have been studied for 80 or 90 years. And so we understand very well the atomic and nuclear structure of many of these systems that we care about. There are more than 3,500 different bound ground states of nuclei. So this is a picture of the nuclear chart. Each one of these squares represents an individual combination of protons and neutrons. All of them are bound systems. The black ones are stable. Everything else is radioactive, more or less beta unstable. So that means that you have a huge fraction of this chart that you can use to select your initial and final quantum states in an appropriate way that you can find the new physics that you're looking for. We also have exceptional experimental control that's really been developed over the past 15 or 20 years through these so-called quantum sensing techniques and other precision atomic methods. And finally, now over the past 5 or 10 years, we're able to produce these rare isotopes with excellent fidelity through a number of worldwide radioactive beam facilities, the newest of which is the facility for rare isotope beams at Michigan State University here in the US. Now, how do we characterize these decays? So typically what you do is you measure the beta particles, or the electrons that are emitted in radioactive decay. You can also measure positrons, which are the beta particle from positron emission. You can also measure things like X-rays, gamma rays, and Bremsstrahlung radiation. So this is typically done in sort of the 100 keV to 10 MeV energy range. But of course, there's another particle that is emitted when you decay. It's just typically you don't think of it as emitted radiation. And that is the transmuted daughter atom that's created in that beta decay process. So beta decay converts a proton to a neutron or a neutron to a proton. But in that case, you means you've created a new daughter atom that is distinct from what you started with. In order to conserve energy and momentum, these have to carry away some tiny amount of energy, even though they're very massive. That energy tends to be very small, much smaller than the amount of energy that we typically carry away in the other signatures of these types of radioactive decays. Now, In both cases, you can actually measure a spectrum. So let's say I want to measure this nuclear recoil. And all I do is measure the nuclear recoil from beta decay. In beta minus decay, I have 3 bodies in the final state. So if I only measure one of those 3 bodies, I get a continuum of energies because there's a continuum of ways that you can share energy and momentum between 3 bodies. So you end up with a system that truncates at the maximum recoil energy of the decay. But in nuclear electron capture, which is an analog of beta decay, you capture the orbital electron in the initial state, and in the final state, you're left with a neutrino and a daughter atom, and the two things here are entangled. So the daughter atom carries the quantum information of the neutrino. Here, there's only one way that you can measure energy, or you get sharing of energy and momentum, and so you measure a peak for the recoil energy that basically is at the single recoil energy that's determined by this daughter. Now, these are very difficult measurements to make because the energies are very small, but if you're able to make these measurements, the recoil is a unique probe of the quantum nature, specifically of the neutrino, as I'll talk about, rare standard model effects, weakly coupled new physics, and you can also search for exotic new particles and interactions. But the key is to make sure that you can actually measure these things to high enough precision. So ultimately what we do is we make a very high precision measurement of the standard model process, and anything that does not conserve energy and momentum has to be new physics. So this, in essence, is what we do, and this is part of the idea of sort of looking for smoking gun signatures of new physics. You may not know what the mechanism for creating this new physics is, but if it doesn't conserve energy and momentum, it probably doesn't fit in our standard model, or it indicates that there's something outside of our standard model. Now, how challenging is it to measure nuclear recoils? So there's 4 examples I'm going to give here, but there are several attempts that try to make this. So the beta decay Paul trap at Argonne National Lab, they measure I don't think that was me. They measure mass 8 recoils, and they take advantage of the fact that in these particular systems, the beryllium-8 ground state is unbound. And so you get high energy alphas that are emitted back to back. And so that your signature is a high energy alpha back-to-back particle. And so they actually set a lower threshold to eliminate beta particles. And this is how they set limits on things like exotic scalar and tensor currents in the weak interaction, which I won't talk about today, but I'll talk about tomorrow if you go to the Right Lab seminar. There's the neutral atom trap at Triumph. So this is called TriNat. Here they use an electric field to accelerate the argon recoils from potassium beta decay to a few keV. This is in a magneto-optical trap. So those are from decays. You can also search directly for interactions to measure nuclear recoil. So this is coherent elastic neutrino nuclear scattering. The first observations from the coherent experiment at Oak Ridge National Lab, they have a lower threshold of a few keV directly for these nuclear recoils. And then there's sort of things like cryogenic dark matter experiments like Super CDMS that measure silicon recoils above 100 electron volts, which they claim is the lowest energy probed so far, and that was as of last year. This uses superconducting and semiconductor detector technology. However, in order for us to measure the direct decay recoils, we have to go a lot lower than this in energy. And our requirements are pretty strict. So as you can see, the case I'm going to talk about is beryllium-7. It has a 57 electron volt nuclear recoil, and the other 2 most prominent cases are much below that. So we have to find a technology that can go to very low direct nuclear recoil energies. Similarly, we can also do the same thing with beta decay, where you measure a recoil spectrum. And for the spectrum of carbon-11 beta plus decay, you're now talking about 90 EV at the highest energy scale where the recoil energy, their spectrum truncates. So our choice is using superconducting tunnel junctions. So these are effectively SIS Josephson junctions. These allow us with a high precision energy resolved measurement. So the way these work is we directly embed the radioisotopes into the outer absorber layer here. When they decay, energy is emitted, and that energy breaks the Cooper pairs of the superconducting ground state. These quasi-particles that are liberated, they tunnel across this thin 1.5 nanometer tunnel barrier. And on the other side, we read out a tunneling current. And that tunneling current is proportional to the amount of Cooper pairs that you broke in the first place, which is proportional to the amount of energy that was deposited. And so here's a couple of pictures of our devices. Here's 1 pixel, and we have multi-pixel arrays. These have a very low energy threshold based on many years of working with the electronics and basically getting ourselves to a point where we can make these measurements. Our low energy threshold for direct nuclear recoils is 2.5 electron volts. We have a very well understood linearity and response of these sensors. And for cryogenic sensing technology, they can actually count at fairly high rates. So we can count at 10,000 counts per second per pixel, which allows us to get to some of these very weakly coupled new physics. We can also think about making direct momentum measurements by loading these radioisotopes into these silicon glass beads that are of nanoscale size. And so here you're basically making a very precise force measurement. And so these are optically levitated nanospheres. This is the type of stuff that Dave has in his lab. And my hope is that I will get to this at the end, but if not, then you can just ask Dave because he knows more about it anyway. Okay, so let's open the Rare Isotope toolbox and start thinking about what it is that we want to put into these sensors. So, as I said before, we want to make a high precision standard model measurement of a recoil from nuclear electron capture decay. So in this case here, we're talking about beryllium-7 electron capture. Beryllium-7 has a Q value, so mass difference between the parent and daughter of 862 keV, and it has a half-life of 53 days. Both of these are very convenient for us. It means we can actually implant things into our sensors, process the whole chip, and then actually cool it down to make a measurement with the superconductor. When this decays, it gives a recoil energy of the lithium daughter atom of 57 electron volts. And we have a neutrino that basically carries away most of the energy, which is 862 keV. And at that energy, a neutrino has a cross-section of 10 to the minus 22 barns, so it doesn't interact in the couple hundred nanometers of our detector. So this is the concept that we use, and the experiment is called the BEAST experiment. So it stands for beryllium electron capture and superconducting tunnel junction. So this is the kind of stuff I couldn't draw on the whiteboard. So essentially what we do is we get a beryllium-7 implanted sample from the Triumph ISAC radioactive beam facility in Vancouver, Canada. This gets directly embedded into the outer layer of our superconducting tunnel junctions. I'll show this process on the next slide. Then what we do is it has a half-life of 53 days. We process the chip. I'll also show how we do that. And then we send it to Lawrence Livermore National Lab, where we cool it down in an adiabatic demagnetization refrigerator to about 100 millikelvin. And we make a measurement while at the same time we pulse in a laser to do an in situ near event-by-event energy calibration using optical photons. So the first two phases of the experiment have been completed. I'll talk briefly about that. We've completed our phase 3 data run. We're ongoing analysis, and I'll show some of the progress of where we are currently at the moment. And just to give you a sense for the scale at Livermore, this is the phase 3 experiment. This is actually the fridge right here. It's quite small and compact. The rest of this is related to the data acquisition and the laser. This is a liquid helium doer. And this is my PhD student, Connor, who's very happy that he's going to graduate soon. So how do we actually produce the beryllium-7? So Triumph uses a method called the isotope separation online technique. And so the way this works is we have a 500 MeV, capital MeV proton beam that impinges on a series of thin production targets. In our case, this was uranium carbide. What happens within these targets is you induce nuclear spallation reactions. So you produce all possible combinations of protons and neutrons that are lighter than the target material. Then what happens is over the course of a few milliseconds, those ions diffuse out of this hot target environment. They enter a cold transfer tube here. We element selective laser ionize the ones that we want. So we laser ionize the beryllium using a resonant laser ionization scheme. Then as ions, we can guide them into our experiment. We then basically guide them through a series of beam lines. We then direct them through a silicon collimator into the STJs, and we put them sort of at around 50 to 75 nanometers deep inside of our material. And this black curve here is actually a measurement of where we put those. So this is a destructive measurement using secondary ion mass spectrometry to see where we put. This is now lithium because they've decayed away. And we compare that with a SRIM simulation, and we get a fairly good agreement knowing that there's probably some stuff on the surface that we can't account for in the experiment. Then what we do is we have to take the chips out. They're irradiated with beryllium and they're open sources, so we're required to take some precautions. We then process the chip, and then we end up with something like this. We just slide it in the mail because in the US, you can just put it to US Post and they mail it to Livermore. Livermore is not so happy about it, getting it in the mail, but it's the easiest thing for us to do. Then what we do is we plug it into the fridge and we measure it. And so each decay, the lithium gets embedded and breaks the Cooper pairs in the superconducting tunnel junction, which we then turn into a signal, and the neutrino goes away. So what we have is we have the missing momentum of the neutrino. We get a discrete peak from the recoil, and anything that is outside of what we expect to see, if we end up seeing something like that, and we account for everything that we think exists, has to be new physics. So this is a picture of what we had. I think this was either phase 1 or phase 2. So this is the 1 pixel. It's basically 120 by 120 micron pixel that's kind of half a micron thick. Because they're so thin, they're intrinsically low background devices. So here's a picture of a 12-hour run. This was actually from many years ago. We have much better control at low energies now than we did before. So this is the number of counts in 300 millieV bins over 12 hours. And you can see that it's fairly sparse depending on the size of the pixel that we use. And we also run, at least for phase 3, we ran a continuous triggerless data acquisition system. So we take everything, sampling at 1.25 mega samples per second over 36 pixels. So we write out quite a lot of data. And you can see that we see things like beryllium events. We see our laser TTL pulse signal. And we are also able to identify what we call substrate events, which are essentially events where we have a decay to the lithium-7 excited state, nuclear excited state, which then gamma decays. That gamma interacts with the silicon substrate that we grow it on. It generates phonons in that substrate. Those phonons have enough energy to break Cooper, propagate their way up, and they have enough energy to break Cooper pairs in the tunnel junction, and they generate a signal. But we can see this in all of the pixels. It's like a bomb going off in the center of the in the chip. And so we can veto these types of events. And it gives us basically about a more than 3 order of magnitude reduction in our decay-induced backgrounds. All right, so that brings us to the phase 3 data, at least the data that we've unblinded so far, just to do our analysis. So I'm going to walk through this a little bit slowly because there's a lot going on here. So the first thing you see is the blue curve. The blue curve results from the fact that we pulse a 355 nanometer laser through a fiber into the cold stage that illuminates the chips. Each one of these little peaks here corresponds to an integer number of 3.5 EV photons that are detected by the chip. So you don't know per pulse how many photons are generated, but you get a statistical distribution of them. And each one of these are exactly 3.5 EV. Well, actually, this number, not quite exactly 3.5 EV, separated from each other. Then what we do is, in anti-coincidence with the pulse TTL signal that we send in to do our calibration laser, we then generate a spectrum that is everything else that we see from the detector. So this is, in essence, our beryllium-7 decay signal. So this peak, I mean, even every time I've seen this 100,000 times, but every time I see this, this is the recoiling lithium-7 spectrum from a kick of a neutrino. So the red curve here, I'm going to walk through it step by step here. The first peak that you see here is electron capture from the 2s orbit to the nuclear ground state of lithium-7. So in principle, you capture from the outermost orbit, right? There's only 4 electrons in beryllium. You capture from the outermost orbit, you leave the atom in an unexcited state, and you just get the nuclear recoil energy. So this is a peak at 56.826 EV. Then you can also capture from the 1s orbit, but now you leave the atom in an excited state. It has to de-excite. That kicks off an Auger electron. That Auger electron we pick up inside of our detector, and we end up with a peak that is energy separated away by the binding energy of the K-shell electron. Then there's, in 10% of the decays, you also get the fact that it can decay to the excited nuclear state, which in essence, an excited nuclear state is a slightly different mass. And so you have a slightly different mass, which gives you a slightly different energy sharing for the neutrino. So you get these peaks at slightly lower energies. Now, this spectrum that I'm showing here is from a single pixel counting for 20 hours at 50 counts a second. This represents 0.1% of the phase 3 data that we took. So this is what we're actually analyzing before we do our unblinding. The full data set is 36 pixels. So here's our full 36 pixel array for 50 days at 50 counts per second per pixel. So in our search for weakly coupled beyond standard model physics, we have about 1,000 times more data than this. Now, there are many things that I was going to step through, but I won't go through all of them. One of the things is that after we took our main phase 3 physics data run, we were able to put it into another fridge that we have that has a little snout on the end of it and surround it by photon counters. What we can do there is we're trying to understand the nuances and details underneath the spectrum in areas that we can't typically access. But what you can do is you can do a gamma tag for the 10% of decays that happen to the nuclear excited state. So you decay from beryllium-7 to the excited state in lithium-7. It gamma decays with a 478 keV gamma ray. If you tag on those gamma rays and project out the recoil spectrum, you can now look only at the the peaks that are generated from the recoiling nucleus that are emitted in the decay to the nuclear excited state. So this helps to clean up a lot of the spectrum underneath and allows us to model better the spectrum. This is work that Connor, my PhD student, basically did over a weekend. We also need to take into account all of the atomic effects. So we have a group in the collaboration from Portugal that basically calculates from first principles all of the different possible combinations for what happens to the atom after you undergo an electron capture event. So you capture an electron, but the 3 remaining electrons now have all manner of possibilities of rearranging themselves within the different orbits, as well as ionizing in some fraction of the decays the lithium as well. And so we calculate this basically because it's beryllium, they can calculate from first principle. But the idea is that we want to include all of these atomic effects. If we're going to be searching for new physics, we need to make sure that we account for as many things as we can. We also embed our beryllium inside of some tantalum matrix. And that tantalum is not pure. And so it's an amorphous tantalum that has many different possible sites where the beryllium can go, but also many different combinations where it sits next to carbon, nitrogen, oxygen, and things like this that will be showing up in the spectrum at some level. And so what we do is we calculate what the possible energy changes are in our spectrum as a function of its location within the material. And then what we can do is, after the fact that we've done the measurement, we can go and we can actually measure atom by atom where the beryllium and lithium sit inside of our sample. It's mostly lithium at this point. So this is a method called atom probe tomography, and this is some fraction of the sample here. And you can see that the lithium inside of the sample is sort of distributed in various locations. And so the idea is that you then convolve the measurement that you make using atom probe tomography with the theoretical information of the materials calculations that you have in order to be able to model appropriately your detector. So this is a painful process, but it is required to do beyond standard model physics searches at the level that we're doing. Also requires a fairly large team of people, only a couple of which are subatomic physicists. The vast majority of people in our collaboration are doing materials theory and atomic theory and radioactive beam physics and things like that. But this was our most recent picture from our collaboration meeting in Livermore. Okay, so what does all this get us? This is a huge pain. It requires a lot of effort. What does this all get us? So the whole point here is to try to understand the properties of the neutrino. So as I said before, neutrinos are at the frontier in our quest for extending the standard model. In the standard model, we typically represent them by their weak interaction states. But the weak interaction states are not the fundamental quantum states of the neutrino. It's just how they happen to interact with our standard model. The fundamental quantum states are their mass states. And when we talk about doing energy and momentum conservation, what we're really talking about is energy and momentum conservation with the masses that are emitted. These two things aren't equal to each other. So the first thing we need to do is, in the standard model, the mass states are identically zero. However, we know from neutrino oscillation experiments, basically these two papers here, that neutrinos do not have, or that neutrinos have mass. At least 2 of the 3 neutrino states have mass. And this is the first and only known violation of the standard model as it's been constructed. The fact that neutrinos have non-zero mass, at least 2 of these states. We know that the mass of the neutrino emitted in beta decay has to sit somewhere in this range. The lower limit bound is given by oscillation experiment, and the upper bound is given by the Catron experiment in Karlsruhe. So if these things aren't exactly equal to each other, then what happens? Well, they're related through something called the PMNS matrix. This matrix here is a rotation, a unitary transformation that I'll talk a lot more about tomorrow as well, that basically rotates between the flavor states and the mass states. Now, what that means is that when I talk about an electron neutrino that's being emitted in beta decay, what I really mean is it's a superposition of 3 different mass states. And so it has a quantum wave packet, and that wave packet has some definite size. And that definite size is determined by, among other things, its energy and the way it's created in nature. So we know these few things about neutrinos. What are the things we don't know? Well, we don't know what the absolute mass scale is. We have a range, but we don't know what it is. We don't know why the masses are 6 orders of magnitude lower than the electron, where all the other things seem to be pretty similar in mass. We don't know whether or not state 1 is heavier than state 3 or state 3 is heavier than state 1. We don't know the total numbers of the mass and flavor states, right? This matrix may need to be extended. I'll also talk about that tomorrow. We don't know if neutrinos are CP violating, and we don't know whether they are Dirac fermions or Majorana fermions. And Majorana fermions would imply that the neutrino is its own antiparticle. So maybe we can actually shed some light on some of these questions using the BEAST experiment. So these quantum properties in the neutrino are not just related to their energy, they're also related to the local environment in which they're created. So I have a neutrino that's emitted in my beryllium-7, and I have a lithium recoil going in the other direction. One of the questions you can ask is, well, maybe we can measure the size of the neutrino. How big is a neutrino, right? We can talk about how big all of the other particles in the standard model are. Some of them we sort of assume are point-like particles, but how big is the neutrino? So what we can start talking about is using the fundamental Heisenberg limit and basically saying, if I can measure the recoil peak at high enough energy resolution, then that implies that I don't have Heisenberg smearing at that level, and I can maybe set some limits on how big the neutrino has to be because the neutrino and the recoil are entangled with each other. So I have my beryllium-7, but I embedded in some kind of matrix, right? This is my tantalum matrix. So it's localized by the matrix that I put it in. And the daughter atom inherits that localization scale, right? It basically knows what the localization scale was of the parent when it undergoes its decay, which now limits its ability when it's emitted to have some certain properties. So the spatial extent of this beta decay-induced neutrino is strongly related to its creation details. And the beryllium atom is localized through its interactions with the complex degrees of freedoms in this lattice, right? It's decohered itself long ago when I first embedded it. But the decoherence of this entangled system inherits that scale that I first had. So can we determine or limit the decoherence scale of this entangled daughter atom via a resolution measurement of the recoil? So our detector resolution is about 1 electron volt. And this resolution potentially allows for sensitivity to this Heisenberg broadening through this expression here, where sigma nu x is basically the size of the neutrino wave packet, and sigma beryllium x is the size of the beryllium that we put it in. So this is the measurement that we make. And there are currently a bunch of conflicting assumptions for what the weak decay localization scale, all the way from the nucleon-nucleon separation energy or separation distance all the way up to interatomic spacing. And this dramatically affects what the size of the neutrino wave packet looks like. And I told my postdoc who I gave this task to, who's recently submitted the article, that I wasn't going to give away his secret in today's thing. So you're going to have to stay tuned, but we have improved the limits on the spatial extent of beta decay-induced wave packets by about 5 orders of magnitude, just from these measurements. Okay, so what else? We're doing momentum conservation and energy conservation with the neutrino. So that means that we can also look at beyond standard model physics mass with the B spectrum. So remember, we have the flavor states and the mass states, and we have this PM&S matrix that connects the two of them. Now, if I plot the mass states, so if I assume this is nu1, nu2, and nu3, each one of these, so I'm looking at them in terms of their mass states, each one of these has some contribution, some superposition of the different flavor states. However, that means that the electron neutrino that I emit is a superposition of 3 different mass states. Now, in practice, these 3 different mass states have tiny differences. So the differences that we would observe from the recoil as a result of this are so small that we're insensitive to them. So we get a peak that is the recoil from the light, mostly active, which are these guys, neutrino mass state. So this is we get 4 peaks in our spectrum, as I showed, but this is essentially the concept that we get in our measurement. However, it's possible that there are very weakly coupled to these electron flavor, heavier mass states, nu4, nu5. We typically call these mostly sterile states. So these are what people call sterile neutrinos, but they're heavy mass states. If that's the case, then in the momentum conservation of our beryllium-7 decay, because the neutrino now carries away a lot more energy, or carries away a lot more momentum because it's much, much heavier, we would see this as an entirely shifted, some fraction of events as a shifted spectrum to lower energies, where that signature would be a result of the fact that there was a heavy neutrino admixture that was observed. So what we search for is a shifted recoil energy and a reduced amplitude, because it happens at a much smaller fraction, or else it would have been seen before. And so in phase 2 of the beast, we actually set the most stringent limits by about an order of magnitude in the sort of few hundred keV mass range. And this was only, what did I say, single pixel counting for 28 days at 10 counts a second. So this was sort of our proof that we could actually do these types of measurements. And this was the result of that. Now, the beast is a phased experiment. So the first phase that we took was the proof of concept. This was basically take tunnel junctions, blast it with a beryllium-7 beam, plug it in and see what you get. And that was, we completed that in 2020. Phase 2 was the results that I just showed. These were our first physics limits that we generated for heavy neutrinos, which currently still set the limit in that mass range. And so this was completed in 2021. We've completed our phase 3 data taking for their scaling to multi-pixel arrays. So as I said before, we have a 36-pixel array. Each one of these is embedded with radioisotope. And so here's where we're going to, we have a number of papers that are on the go, and most of them should be completed this year. And finally, we have a phase 4 where we're going to go to aluminum-based STJs, which give us a slightly higher energy resolution, we think. And we also are going to find ways of implanting higher doses into each of them, and we're going to operate them continuously for many, many months in a dilution fridge. So this is kind of, here's a picture of one of the prototypes for the phase 4 128-pixel array. Now, we're talking about measuring neutrinos, potentially neutrinos that are on the right mass range to be considered dark matter. And so it's a natural connection between what we can measure in the lab and cosmology. So this dashed line right here, so I guess I'll lay this out here. So this y-axis here is the relative fraction of the coupling of these heavy, mostly sterile neutrinos to the electron flavor. And this is the mass of that neutrino. So going all the way from EV scale all the way up to TeV scale. This dashed line here represents something which is the so-called canonical seesaw model. And so this basically is one of the possible models that generates heavy neutrinos if you want to extend the PM&S matrix, which I'll talk a lot more about tomorrow. So phase 4 of the BEAST aims to be the first experiment in this mass range to really probe into this canonical seesaw model. And in this mass range, it's also a dark matter candidate. So it can't be lighter than this, or else it's excluded basically by the fact that you can't cram enough fermions of a light mass into the dark matter halos for it to satisfy the mass conditions. And if it's too big, or sorry, if it's too heavy, then it means that its phase space for radioactive decay into other neutrino flavors is far more likely, and it wouldn't have kicked around in the universe until the times today. So this is kind of the region that we search for, and this is what we are planning to do in phase 4 and beyond of the BEAST experiment. There's also another a series of other precision beta decay experiments, including the extension to the Katrin experiment, that we work closely with that group to basically try to cover the range between basically 1 keV up to 1 MeV using laboratory measurements. So there's all manner of other things that we are searching for in the BEAST data as well. So for example, we're sensitive to all new physics that couples to the neutrino mass because we're looking for non-conservation of energy and momentum. And so things like new bosons that are coupled to neutrinos can address certain problems in cosmology. So this is work that's theoretically been done by our colleague at Triumph, Dave McKean. And so this experiment here would basically be the emission in our BEAST data of 100 keV or a 300 keV Myron. The dashed line is what he calculates, and then convolved with our detector resolution, we get something with the solid lines. But the idea here is that basically this generates some kind of a 3-body component to our decay because it's being emitted. And so we get our 2-body component, and then at lower energies, we get some kind of a 3-body component. So this can be extracted, limits on this can be extracted from our phase 3 data as well. Yep. Yep. Yes. Yep. Yeah, okay, so for the first one, we're very confident that the energy stays inside of the detector. So if I go back to this one where we actually showed the implantation profile. So the first thing is that we're talking about at maximum 50 electron volt recoil energies. And so at that energy, a heavy ion travels about 1 atomic unit. So they don't go anywhere in the detector. They basically, it more or less perturbs the region that it's around. And we can measure where we put these things. So we know that they're well within our detector. The second question is more complicated. So the short answer is, so we do, as I said, almost a near event by event energy calibration. So we're constantly pulsing this laser at exactly the same time that we're making our measurement. That allows us to make sure that the detector is functioning the way we think it is. It makes sure that the energies are not drifting as a function of time, making sure. So, but the one thing that we are not certain about is the absolute energy scales relative between the two of them, because there could be some quenching effect of the superconductor where a nuclear recoil generates a different number of quasi-particles per unit energy than the photon does, and they sample different parts of the superconductor. So that would basically mean that there could be some small absolute offset between the two. But in our case, we don't care necessarily about what the absolute energy is. We just want to make sure that relative energies aren't changing. And so the way we do this is through a constant sampling of this from the laser. So that's more or less how we've tried to set it up so far. But there are a number of things, especially the atomic and materials concerns that kind of make it challenging for us to do that. Okay, so that's what we do with beryllium-7. But there's nothing special about beryllium-7. In fact, one could say, well, I just started at the beginning of the chart of nuclei, and I just pointed at something that was close to the front and said, why don't we study that one first? Most of the interesting cases that we care about for beyond standard model physics searches actually are at heavier masses and are much shorter lived. And so this is what, as I keep saying, this is what I'll talk more about in detail tomorrow. But in order to go to shorter lived things, we can't use the beast concept in the way that we've done it. I can't implant something that has a half-life of 300 milliseconds, process the chip, put it in the mail, ship it to Livermore. It's not going to work. So now what we have to do is we have to couple our fridge, set up all the detectors to a radioactive beam line and do the experiments at the facility in situ while the beam is being implanted. So this is what we call SAILOR. So this is the superconducting array for low energy radiation. All these images are generated by GPT. So what we do is we have a beam line that exists at the facility for Rare Isotope Beams. We take our snout of a detector. So if I go back to this, you can see that there is a little snout on the end of this thing. There is a detector right at the cold stage of this. This detector goes into the beam line. We have a series of windows that basically thermally isolate the cold stage from 300 Kelvin, and we directly implant the radioactive ion beam into the chips. Now we can access nuclei with half-lives of 10 milliseconds or larger. And it means that we can also control the depth of where we place this thing just by moving some kind of degrader. So SAILOR at FRIB is the first attempt at using short-lived isotopes in these active sensor arrays. So here's a picture of what it looks like at Star Cryo-Electronics. It's going to be delivered, I think I have that on one of my next one. It's going to be delivered next week to FRIB after a couple years of planning. And this is more or less the way that the setup looks. The beam comes in. We have some kind of diagnostics box here. We have our fridge with everything located on it. And for those people that know FRIB in any way, this is located in RIA 3, one of these setups. So this is our laboratory space here. This is the construction of the fridge, which now has been, this is the soonest pictures I had were from December. But the fridge has been tested and it performs very well. Last week, one of my PhD students, Drew, basically tested the initial STJ array that's going to go to FRIB next week. We had 28 of 32 pixels that showed very high performance. In fact, this is probably the best performing STJ we've ever made. And so we get about 1 EV resolution at 100 EV. And so this is kind of the next phase that we're trying to go to. And this helps us provide additional weak interaction tests for much shorter lived isotopes. Again, stuff I'll talk about tomorrow. Okay, and finally, I'll briefly go through these radioisotopes into the nanospheres. So one of the things that we're always going to be limited by with the superconductors is this materials effect that I showed before. No matter how much effort we put into understanding the location of the radioisotopes with respect to everything in that lattice, we're never going to understand it perfectly well. So instead of moving to an energy measurement where the energies get very complicated inside the superconductor, we can actually go to a force measurement and measure the momentum directly. So in this case here, this was work that Dan Carney at Berkeley and Dave and myself did kind of during pandemic times, I guess. We basically thought about this idea of what happens if we take these spheres that Dave has in his lab and we dope them with radioisotope. And so the idea is that you put a radioactive material inside of them, and when a beta decay happens, the whole sphere gets a momentum kick as a result of the fact that the recoiling nucleus stops within the sphere, and then the whole sphere center of mass moves. And so this was fairly crazy, but it seemed like people liked it. And, the paper was fun to write. So in the end, we thought, well, what can we do with this? If we want to search for these mostly sterile mass states like we do in the BEAST experiment, you actually have fairly good sensitivity. And even with just, I think, loading 1% of the sphere with the radioisotope of interest, there's a few of them here, and only counting for a month, we got limits that were already very competitive with what's currently exists. And in fact, the beauty here is that you can actually think now about doing things with beta decaying isotopes other than just electron capture decaying isotopes, which now widens the possibility for case selection that you can think about. And finally, we got to the very speculative thing of trying to measure the very light neutrino masses. So these are sort of tens of milli-eV masses. And here now you actually have to play uniquely quantum tricks, and you have to squeeze the center of mass well beyond the standard quantum limit in order to basically get the sensitivity that you need to measure these light neutrino masses. But again, it's part of this concept of trying to use the coupling of these modern, truly quantum sensing methods with radioisotopes to try to find new physics. Okay, so after all of the rigmarole of both rooms and everything like that, conclusion. So the frontier of new physics really requires a strong connection between cosmology and the lab. And in order to do it in the lab, to probe at the sensitivity levels that one can reach with cosmology, you really need to generate the new physics yourself. And the way we do that is through the radioisotopes. We get huge amounts of radioisotopes, and we generate any new physics that would result from that, even at a very weak probability scale in the laboratory. Neutrinos provide a unique window in how the standard model is broken, and maybe our best way to exploit this connection at the moment, both based on how we can make the measurements in the lab and with cosmology, but also where it fits in the standard model and why the standard model looks the way it does. And we're doing this in a couple of ways using superconducting sensors with BEAST and Sailor. Hopefully in the future, we're going to use these doped and undoped levitating spheres. And with that, I'll just advertise that we always have positions open. So for people who are looking, especially for postdocs, please send me an email. And with that, I'm happy to take questions.
Taylor experiment, you know that the relaxation from implantation is over.
Yeah, so we've tested it already. We've tested that concept. So we can hit it with stable heavy ions and see what the response is. And so it relaxes back to its state where it can take a new measurement in about 100 microseconds. And so for us, that seems to be fine. At least we think. We will test it, of course, once we get it there. But we've seen the pulses and the signals, and it relaxes back to a point in between 100 microseconds and a millisecond. So. Very similar, yeah, very similar stuff. So if I go to this and I find that slide again, I mean, that's a great question. So and not off topic at all. I think it's perfect. This one here. So okay, so the beta decay Paul trap, it searches for new descriptions of the weak interaction. So the weak interaction is in principle a vector minus axial vector interaction in the standard model. There's no fundamental reason why that should be the case. So they search for, in this particular one, they search for potential tensor contributions to the axial vector part of the weak interaction. And using other forms of methods, also using recoils, we can search for potential scalar contributions to the vector part of the weak interaction. So that's that one. The second experiment at TriNat, I mean, they search for a lot of different things, but in principle, they also search for new descriptions of the weak interaction. They use the recoil and the electron to measure a beta neutrino angular correlation. And so you can correlate the angles of the beta particle and the neutrino, even though you don't measure the neutrino, but you measure the recoil. And because, again, we think nature has to conserve things like angular momentum, then that means if you measure something that you don't expect, it can signal new physics. The other two are direct detection. So coherent elastic neutrino scattering, I mean, there's a huge range of physics that you can search for there. But basically what you're doing is you're exploiting a coherent effect where the neutrino actually scatters coherently off of an entire nucleus rather than a single nucleon. And so you get a higher measurement cross-section for the neutrino than you otherwise would using basically just a neutrino. And then the final one is basically a dark matter, a WIMP dark matter search. Yeah. 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 So so you're absolutely right. So we have a low energy threshold right now of 2.5 eV. I think it's extremely unlikely that we would go below that. For us, it's sort of okay because the signals that we want are all well above that. The dark matter community always wants to push down to lower and lower energy. So, but for us, we know the point of these experiments is we know very well what the energies we expect to be, and they're sort of the smallest energies we see are from the L capture to the lithium excited nuclear state, and I think that's something like 13 or 14 electron volts.
I didn't see isolated plots.
So we do not search for EV scale ones because we're totally insensitive to that. Actually, let me do this. But I do have a plot here. I think this is the one I want to show. Yeah, so if I think about, so EV scale is sort of in this range here. Basically, so at least on this plot, they don't include, so this is from basically a compilation of these things. But here they basically show the cosmological measurements, so CMB and things like that. They don't seem to show IceCube. Don't really know why. But yeah, I mean, the definitive measurements in the EV range, in my opinion, are going to be things like the Katrin experiment, which will push this down further. So. We did it.